the time I want to give to this. I'm also going to tell you something about the way that I run pop quizzes in this class. I don't collect them. Instead, I'll ask you this. Does anyone feel unhappy with their proof? Cool, then we are going to talk through this now. I'm going to start with a similar pop quiz on Friday. So if we're all happy, let's talk through the proof. And let's start just like with the anatomy that a proof of the sort of plane has to have. How should we start this proof?
2 set containment, so you want x to be on one side and shows on the other.
Yep, and it's only 1 set containment. These 2 sets are equal, but I'm only asking you to show one of the 2. So let's assume x is in the set that's a legibly smaller. And that's really like the second line I'd want. Really what I'd like the first line to be is of course, that being said, if I don't give you 5 minutes, maybe some things really special. Okay. So there's what we get to know. We know that x is an element of the pre-image. What's our goal?
Show that x is on the right side.
All right. So how do you go between those 2? I guess we better start unpacking things. So hopefully people started by looking at the definition of what pre-image means. What does it mean for x to be an f inverse of y? Yeah.
That means that there's some y in y1 union y2, like such that y equals f of x. Or no? Or did you go the other way?
Almost. Wait, no, I think what you said was right. So I'm going to write that down and then we'll simplify that. Yeah, what you said is correct. So there exists some y in y1 union y2 with f of x equals y. Yeah, you can say that in a quicker way by not having this allusion to there exists some. You can just say, so f of x is in y1 union y2. Sorry, since y is equal to f of x, you don't need to be so mysterious about there exists some. You can just say that's the thing. So what you said is correct, and I think probably the proof will walk out fine from there anyway. All right, so there's what you know. Either expand out the thing that you know, or look at the goal to try to expand that out to figure out what you need to show. So,
I just expand out the first one, right?
cool, let's expand out the first one.
Alright, so then f of x is in y1 or f of x is in y2.
Cool. How many people had followed roughly this plan so far? Nice. And I guess if you followed your plan, it would have been y in that set, which would have been fine. Cool. What next?
Can we say that then there's an x in f inverse of y1 or x in f inverse of y2?
Ooh, I don't think you need to be existential. So you're gonna like walk in cases?
Mm-hmm.
So let's label these case 1, case 2. In case 1, f of x is in y1. So you already know what x is. X is declared there. So you don't need to be mysterious saying there exists. F of x in y1 means x is in f inverse of y1. That feel okay? Oh, cool. Let's finish up this one case. So if x is in f inverse of y1, how can you get that? If x is in f inverse of y1, how can you get this conclusion? Is it basically automatic? Yeah, unions make sets bigger. Since x is in f inverse of y1, x is in f inverse of y1 union f inverse of y2. So we are done in this case. How would, so in case 2, x is instead in f of x is instead in y2. Does case 2 differ from case 1 in any way? Replace the 1 with 2's. In case 2, the same argument gives x in f inverse y1 union f inverse y2. So either way, yeah. That's my proof. Yeah.
Can you do like a proof by contradiction? And just basically do this but like the opposite, like you're saying. You know what I'm saying? Like, yeah, like there's something that exists in the bigger group that isn't in the subset. And show why it's false.
Something like that. I may have lost the words, but you want to suppose there is something in the smaller set that is not in the bigger set, and then get a contradiction. That would do it, right? Let me see this.
I don't remember what was.
Oh, because you were putting equality.
Oh,
Okay.
no, this was right.
Oh, okay.
I mean, the proof of that, I just mean like could we use a proof?
Yeah.
Okay.
Yeah, I'm sure you could. When you finish with the proof by contradiction, you could probably be able to extract the direct proof out of it, but that doesn't mean you can't use a proof by contradiction. You know, I'll ask a similar question. Right? Not the same question. You've already seen this one. Similar question. That being said, this was slightly improvisational, and now I find myself 25 minutes behind where I want to be right now. But c'est la vie. Let's talk about algebra. So we have like some of this background about set theory and stuff, and we'll use that a bunch. But now I want to start like actually studying the real numbers. And like, it would be really annoying if your definition of the real numbers are like things that have decimal approximations. Just like everything we understand. Instead, for me, the real numbers are given by the following conditions. The real numbers are a complete ordered field. And we said something about those words like on day 1. But roughly, what do these conditions mean? The fact that it's a field just means it's a place you can add, subtract, and multiply, and divide. The word ordered means there's an inequality. You can talk about the order that the real numbers come. the word complete somehow says that there's nothing missing. Like pi in some sense is missing from the rationals, but it is in the reals. And we'll make that explicit once we get to section 2.5. So for now, let's talk about the field axioms. So the field axioms just say that a real numbers, well, a field, is a set together of two operations plus and multiply, satisfying the following. Plus and minus are binary operations. That just means that plus and multiply take two inputs and give one output in the field. They satisfy the associated laws. And I mean, you know what the associated law is. X plus y plus z is the same as, what does this associate?
X plus y plus z.
Yeah, it says that you don't need to pronounce the parentheses. And we'll use that a lot just implicitly. You can't make sense of x plus y plus z without parentheses, without the associative law. These operations are commutative. X plus y should be the same as same with multiplication. So far, so good. Those better be things that are true about the real numbers. Multiplication distributes over addition. Well, you know what that means too, right? And you can do it regardless of whether you're multiplying on the left or the right. There is an axiom of the additive identity. So let's read this out. There is an additive identity called 0. Maybe I'll make this explicit. It better be an element of this set we're talking about. Such that for all elements of the field, 0 plus f is f plus 0 is, yeah, right? If I add 0 to something, I better get the same thing back. And these are all axioms, so I'm not going to try to prove them. These are just things I will assume. There is a multiplicative identity called 1, so that f times 1 is 1 times f is also f. The law of additive inverses. For any f, there's an additive inverse called minus f. I mean, you know what I'm going to put in that line, right? When I add those two things together, I should get the multiplicative identity, no, additive identity, which appears in item 4. Law of multiplicative inverses. For every f other than 0, there's a multiplicative inverse called f inverse, so that when you multiply it by f, you get 1. That feel pretty good? All right, so those are just the axioms. It turns out these are all of the things that you need to know about the reals to do all of algebra, which, neat. In fact, you can get away with less than that. Do you think I needed to be able to distribute on both the left and the right? If I could do it on the left, I could use commutativity to get the right. So this isn't like a minimal list of axioms. There's some redundancy. But let's use these. Okay, so subtraction. You know what subtraction means? It's add the inverse. You know what division means? It's multiply by the multiplicative inverse. The first axiom of the real numbers is as follows. The real numbers are a field. So what's going to happen with the rest of this section? So all the rest of today and probably a chunk of Friday. Let's use these field axioms to do some stuff, to prove the rest of algebra. And maybe I'll start by taking a tour of what's in here. So the first thing that I want to do is talk about uniqueness. So the axiom that there exists a 0 doesn't say 0 is the only element that behaves like 0. But it would be weird if it weren't. If there was some other element that you could add to stuff and it always stays the same, that would be weird. You know that doesn't happen. But it's not in the list of axioms we need to prove. Let f be a field and 0 hat and 1 hat be elements of the field. If 0 hat plus x is equal to x for all x, then 0 hat is actually equal to 0. Fair enough? Same with multiplication. Similarly, it would be weird if additive inverses weren't unique. Like if there were something else you could add to f to get 0, that other thing should just be minus f. But there's nothing in the axioms that say that, you have to prove it. So we'll prove that. The last thing we'll do in this pack is we'll close by just some properties that involve what minus does. And we'll prove these things just using the axioms. That seem like a reasonable set of goals? So these will be like very different feeling proofs from the set theory stuff we've been doing, but they should feel reasonably light. So let's prove this first thing. And in fact, I'm only going to prove the one about 0 hat. The one about 1 hat is left to you. And maybe as we do this, think about how you would adapt the proof for 0 hat. So let's do it. So start with the assumptions. Let 0 hat be an element of f. And let it satisfy that for everything in f. 0 hat plus x is equal to x. So just declare the assumptions. I want to show that 0 hat is actually equal to 0. And here's the strategy that's going to be used in this particular one. We're going to expand out 0 plus 0 hat in some different ways just to see what we get. So on the one hand, by our assumption about the behavior about 0 hat, what should 0 hat plus 0 be?
0 hat.
That's one of the two things. But that uses the behavior of 0. So like that would be the answer to the next line. Which is, 0 hat is a thing that when I add it to anything, I get that same thing back. So 0 hat plus 0 will be 0. On the other hand, what you said is also true, right? 0 hat plus 0 by the axiom of the additive identity. What do you get when you add 0 to 0 hat?
0 hat.
Oh, cool. So these two things are both equal to 0 plus 0 hat. So they're equal. So that's like a sneaky proof, right? There's like a clever and subtle step, like an idea you need before you can get started. In this case, it was take something, some weird formula, 0 plus 0 hat, simplify it down in two different ways. The two things you get should be equal. So this is a clever idea and something to like keep in the back of your mind if you want to prove some algebraic result. See if there's some complicated thing that should simplify down in two different ways. And we'll see this idea a few times today. Do you think you could do the same thing for 1 hat as well? How much do you think the proof would change? I think some pluses would become multiplies. Yeah, I think you could do a literal copy paste and change some laws, right? Groovy. All right. So we're just going to go through and prove some algebraic results. Let's keep on going. Here's a fact. What should I get if I multiply something by 0?
0.
Cool. Is that in the list of axioms?
No.
No, I only know what happens when I add 0. So, let's try to figure out why this should happen. So there's some guidance there. Like I'm going to use the trick of adding 0. But instead of doing it there, let's do it on blank paper. We need to show this. So let's see, a times 0, like that's definitely true. I can add 0 to something and get that same something back. Let's mess around with this though. Like that looks like it's close to being in a situation where I could like factor out a 0. And factoring is just the distributive law, it's just done backwards. Can I factor out a 0 yet though? Is that 0 times something?
No.
Sure it is. It's 0 times 1. Let's use that. So let's use that and we can get away with using, well, factoring. A times 0 plus 1 times 0. That's what I want to be doing. Oh, god damn it, I'm doing it wrong. All right, well. Because then I'm just going to wind up with a plus 1 times 0. That's not helpful. That's what I get for trying to do things out of order. Where am I? Oh, screw it. Okay, no. Doing it organically doesn't work. All right, let's follow the guidance here. So let's play this game. We'll add 0. That's the same thing. Let's also use the fact that a minus a is 0. So that means I can replace that 0 with a minus a. Now that looks an awful lot like something I can factor an a out of, right? But same trick, I don't literally see a times something with that second a, but I kind of do. How would I write that a as a times something?
A times 1, cool.
Okay. All right. So by the axiom of the additive identity, no, I'm using the multiplicative identity. I can replace that a by a times 1, minus a still sits around. The distributive law lets you factor. So looking at that a times 0 plus a times 1, how could you rewrite that, Aaron?
A times 1 plus 0, or 0 plus 1.
Cool. And then I still have this minus a floating around. And you know what, I think I actually want more space. All right, so you're looking at that, you want to keep simplifying. The eventual goal is I want to get this down to 0. Does that look like something that should be equal to 0? Nice, now you just need to convince me why. What more could you do to simplify that? Times 1 minus a. Cool, that is true by the law of the identity. So I'm going to put a comma there just for the sake of language, and additive identity to get a times 1 minus a. Is that looking more like 0?
Mm-hmm.
Nice. All right. Finally, by, let's see, so far I have this equal to a times 1 minus a. So what more can you use to get that down to 0?
Multiplicative identity.
The axiom of the multiplicative identity. Law of multiplicative identity. A minus a. What next?
Was it just follow it that it equals 0, or?
Yeah, but there's like a name for that axiom.
Oh, like the inverse or
Yeah.
something.
And law of additive inverse. That equals 0. Oh, cool, that's what I wanted. That completes the proof. Groovy. So in this case, the game was like, take the thing you want to be 0, make it look more complicated. That gives you space to try to simplify. If you're sneaky about how you simplify it the right way, you can get down to this claimed identity. And you'll notice that this time I'm being like really explicit about exactly what rule I'm using each time. For the homework associated with this pattern, I want you to do that. Once we're past this, I don't want you to do that anymore, because otherwise all of your proofs will be like 2 pages longer than they need to be. That feel okay? Nice. All right. Yeah, we're plugging along okay. I said we'd show that inverses are unique. In fact, like, let's just read the first couple lines of this argument, and then we'll see if you just believe that it should work out. So I think maybe we'll even like put the things in the space here, and then figure out what would go in the line for justification. So let F be a field, F and G be an F. We're going to assume that F plus G equals 0 because that's what this theorem 2.1.1 says we get to assume. We want to show that G is equal to minus F. So let's start with F plus G equals 0. How would you want to show that using that fact that G is equal to minus F? Well, does this seem reasonable to like add minus F to both sides of that equation? And you can, right? Part of the thing about being a binary operation is that it's well defined. If two things are equal to each other, when you add them together, the results are still equal. So let's add minus F to both sides of this equation. I guess I'm adding on the left. That's going to give me minus F plus G equals minus F plus 0. And now, so that's an equation that follows from the assumption. Good. Let's try to simplify down both sides. What is the right-hand side equal to? Cool. And I know there's this blank, but like, there. So that's good. The right-hand side reduces to minus F. If the left-hand side reduces to G, then we win. So we have a goal in mind. Take this, which I wrote down incorrectly, but it is the same, right? And let's simplify that down to minus F.
Yeah, so can we first use the associative identity to say that minus F plus F parentheses plus G?
The associative law minus F plus F, parenthesis, plus G. Cool. Why is that helpful?
So let's put the F in minus F in parentheses, we can use the inverse law to cancel it out.
So by the associative law, by the law of additive inverses, that becomes 0 plus G.
And then using the additive identity with
And the law of additive identity. That is equal to G. Thus, as G is equal to minus F plus G is equal to minus F plus 0 is equal to minus F, what do we conclude?
G is equal to minus F.
Which is good, because that's what we needed to do. And again, how much do you think this would change if you wanted to show the same thing for multiplication? Not at all. Groovy. Nice. Oh, so like, I'm actually in a better place time-wise than I was expecting. We might not be able to finish all of theorem 2.1.5, but that's okay because most of theorem 2.1.5 is homework anyway. So, let's try to prove some of theorem 2.1.5. And my intent is, in the notes, we prove 1, 2, and 3. These two equations for 4 and equation 5 are for you. So, let's make the progress we can. And in fact, in order to prove this force, well, let F be a field, let A and B and F. Item 1 doesn't actually involve A and B at all. So I won't declare A and B yet. Let F be a field. We want to show minus 1 quantity squared is equal to 1. Let's try to come up with a plan of attack. I actually care about the recording today, so. There's the thing we want to show. Right, and hopefully in the notes the definition of squaring appears right above the statement. Does it? Oh yeah, x squared is just defined to mean x times x. So, all right, let's see what we can do. Here's the thing we want to show. So in order to come up with a plan, let's imagine we like simplified this equation somehow. And eventually we can get it down to a truism, there's our proof.
Can we go left -1 times -1?
Cool.
And can we make each -1 times 1?
So like that. That certainly is true. So maybe I'll suggest this. And this should be like strike memories from your like doing things in pre-calc way. Maybe it'd be nice to have all of the complicated stuff on the same side. Because then maybe we'll see like something that factors or something. Let's put everything on the same side. So let's like subtract 1 from both sides. That follows, right? Maybe there's some steps, but that's okay. We just need to sketch right now. All right. Does this make you think of anything? Maybe some factoring? Or like, I certainly see a -1 in both of those pieces, right? So the distributive law lets you factor, as long as that -1 is -1 times something.
So can we pull out a -1 and then say we have -1 times -1 plus 1?
Yeah. And in fact, the intermediate step there, because now I definitely can do that.
And then using the law of additive inverse. Did we prove that earlier?
Yeah, and in fact, maybe I'll even say what we're citing, the result was called theorem 2.1.3. Cool. So, the actual proof then is going to be this, but backwards. So, let's try to write the proof down. I think this is going to be different enough from the order of things that are written in the actual, like, fill in the blanks. Then maybe I'll just start at the bottom. Proof of claim 1. So I'm going to follow that's written here, starting from the bottom. So by theorem 2.1.3, -1 times 0 equals 0. And now what will we do? Let's describe the steps going backwards. So how do you go from here to there? Yeah. So by the axiom of additive inverses, 0 equals -1 times 0 equals -1 times -1 plus 1. All right. So that gets there. How do we get this next step?
Axiom distribution.
Yeah. By distribution, this gets us -1 times -1 plus -1 times 1. Cool. What goes on in this next step?
Multiplicative identity.
And multiplicative identity. All right, so far so good. In this next step, we actually change both sides of the equation, so I really need a new line now. How do you go from here to there?
And then inverse.
Sorry, my phone made noise. Say again?
And then inverse again.
Yeah, you're going to, well, let's add 1 to both sides and then use the law of the additive inverse, because that's how you get the 1 on that side. Add 1 to both sides and use, so that's 0 plus 1 equals, gosh, -1 times -1 plus -1 plus 1. Yeah. What next?
Now it's additive.
Additive inverses. And you know what? I'm getting tired of writing -1 times -1. All right, so we're getting closer. So why should this imply that -1 squared is equal to 1?
Additive identity.
Thus, by the axiom of additive identity, 1 equals -1 squared, and we're done. Cool. That seemed pretty okay? And I guess we don't have many other ones in this list. But really this gives you an idea of how to come up with like these purely algebraic proofs. Start by like pawning on the like part of your brain that you remember from like those 2-column proofs from trigonometry. Maybe you can notice. Yeah, it was a while ago. But the proof you wind up writing is actually backwards of the proof that I want to see. I want to see a proof that starts with something you know is true and ends with the thing you want. So do this, and it'll get you the backwards of what the proof I actually want is. Now explain how to do it backwards. Neato. Cool. So I'm past time. Anyone plan on coming by my office hour today? Cool. You don't need to tell me if you are. If you change